Now we're going to talk about the idea of subgroups and isomorphism. Okay, it sounds quite complicated, but it's really very easy. Okay, let's take our group, RF, the reflections in two-dimensional plane, and we explored the last time the fact that this is a group. We proved more or less that this is a group. It satisfies all four conditions, and it's also an abelian group because it's commutative. Okay. Let's answer the question of what happens if I take a subset of this group. Okay, so let's call the subset RF dash, and let's take the elements I and RF naught. So a subset is just taking a couple of elements from the main set, but not all of them. Okay, if that's forming a subset, okay, it's fairly obvious what the concept means. This is the set, this is the subset, okay? The question now is, does this subset form a group? Okay? Does this subset form a group? Alright, well what we can do is, we can explore its multiplication table. So this one is a little bit easier because it has just two elements. Okay, so let's put I here, RF0 here, I, RF0. And the binary operator is just combination. Okay? So I times I is I times RF0 is RF0, RF0 times I is RF0, and RF0 times RF0 is I. So it's closed, it is closed under this binary operator. Okay, and as we saw the last time, all of the other conditions for a group are also satisfied. Okay, there is an identity, they're their own inverse, and it is associative. Okay, so this subgroup is also, or this subset I should say, is also a subgroup. Okay, so what we can write then in the language or in the notation of mathematics is we can say that RF dash is a subgroup of RF. Okay? This is the notation meaning subgroup. Okay? So we know that RF dash is a subgroup of RF. Okay? What's interesting though now is to explore a different group altogether. Okay? I'm going to take the group of even and odd numbers. Even and odd integers, let's say. Okay? Even and odd integers. We can do out the multiplication table the same as always. Okay, we have E. Actually, in this case, it's still called a multiplication table, but you can see why it's maybe better to call it the Cayley table, because the operator I'm going to take is addition. Okay, so I'm going to take addition as the operator. Okay, so let's do out the Cayley table. An even number plus an even number will get you an even number. An even number plus an odd number will get you an odd number. An odd number plus an even number will get you an odd number. But this is the crucial part, because an odd number plus an odd number will give you an even number. Okay? So you can see this is also a closed set. It is in fact a group. Okay? But you'll notice if you compare these two groups, you'll notice that they're very similar. Okay, the operator is different, but the structure of these groups is the same. Okay? In fact, the group structure is identical. Okay? And what we say in the language of group theory is that these groups are isomorphic, having the same form or the same shape is what isomorphism means, same form. Okay, so these two groups are isomorphic. Okay, there's a couple of other groups that are also isomorphic to these two. You could take the elements 1 and minus 1 under multiplication. you'll get a similar table. You could also, and we'll see this in the coming videos, you could take the identity element and rotation of 180 degrees under combination. These two groups are also isomorphic to these. Okay? So this is the lingo, right? Groups we say are isomorphic if they have the same form like this, and this is the notation for a subgroup. So RF dash is a subgroup of RF. Okay? They call this group here that describes the structure of all of these groups, they call it, where's my blue pen? They call it Z2. Z2. The reason they call it Z2 is because Z implies it's a discrete group. Okay, there's only a discrete number of elements. Okay, and this is inspired from, of course, the Z symbol for integer numbers. Okay, this 2 here then means 2 elements. 2 elements. Okay, so you can see in each of these groups there's just 2 elements. So this is the group Z2, and they normally write this group as Z2 is IG. Okay, IG, with the extra condition that G squared, of course, must give you back I. Okay, so G just stands for any element that isn't the identity element in Z2.